which is given some examples. So from NeuroNEXT, which as I mentioned yesterday when we introduced the network, it's a network that does kind of phase 2 learning stage type designs. And so given that it's comparable to what a lot of you are probably working with and some of the issues you're struggling with in your proposals, just to kind of talk like case studies perspective of a couple of things from the NeuroNEXT perspective. One, as was alluded to when Eric gave his introduction yesterday, in a lot of ways, designing these learning stage studies are the most difficult. Phase 3 trials are difficult to run. In some ways, they're kind of, if everything was done well coming up, they're kind of easier to design from a statistical perspective because you kind of know what the question to ask is that you're trying to confirm. It's a little harder in phase 2, mostly because of some of the issues we talked about. How do you make sure that you're getting meaningful information that will lead you forward? And I think one general thing to keep in mind is really, and this is a kind of a change from academic trialists in the way they're thought, but in industry perspective, you often think of a trial as part of a full drug development program. And each study that you do has a purpose in terms of where that program is moving along. Traditionally, academic trials haven't thought in that way. I mean, it's all, this is my grant, this is the study I'm doing. But particularly when we push investigators to think more when they've worked with us in the network, is where does this fit in that program type space? So for instance, if you're doing a phase 2, as Eric mentioned yesterday, what's the next study look like? Where does this fit into what you need to know for the next trial? The second piece of that is then just give some examples of some of the types of ways that we've addressed that in the network. So I'll kind of give you a flavor of lots of different designs. The biggest aspect, and this kind of reiterates the point, I kind of use this picture to illustrate it, in confirmatory designs, even in terms of doing it, because they're so large, and this probably shouldn't be the case, but it kind of is, in that you can be a little sloppy in a large clinical trial, a little sloppy with your data management, a little sloppy with how you're collecting data, maybe not use things as efficiently as possible. So for instance, a common thing is you might collect your outcome quarterly over a 2-year period, and your primary endpoint is a change from baseline to end of study, not really accounting for any of that intermediate information, which is, from a statistical perspective, you're throwing away information that would perhaps be better engaged in looking at that. You can kind of do that in large studies, and it's commonly done in large studies and get away with it. Versus in learning stage designs, particularly if you're in areas where you're limited by the sample size, which many of you are struggling with this, if they know in your proposals, efficiency is critical, right? So if you're capturing things multiple times, you really want to take advantage of modeling things longitudinally to try to squeeze every ounce of efficiency out of the study. And then you put this up here, it's kind of like if you're one of these little kids running in this race and you fall down, there's so many kids, probably half of them are going to fall down and nobody will notice. When you're out running by yourself, coming to the finish line, if you trip and fall, it's going to be an interesting story, and you may go viral on social media. And so you want to avoid your trial going viral on social media because it's the design that falls on its face. In kind of in broad sense, to think about, and one of the biggest challenging things for phase 2, where you are limited in terms of size and complexity of what to do, it really doesn't change the main premise of what you want to do in trials in the first place. So every clinical trial should examine an important question, right? What is the question that that trial is setting out to do? And as you've heard multiple times throughout the last 2 days, a successful trial is a trial that answers the question of interest, right? One way or other. You're looking at the drug, does it show the drug works? Does it show that the drug doesn't work, it's not worth pursuing further? If you answer that question, then you've done a positive trial. If you get to the end of the trial and you know no more than you knew before, that's what I would term a negative trial, right? You spend all this time and resources and you really don't know anything more than you did before. You might pretend that you do, and we're really good at telling back stories to justify why that is, but you likely don't. You should design the trial in such a way that you're minimizing risks and you have methodology in place to answer that question, right? So one of the most critical first things that comes up, and this is what in probably the first webinar, maybe the first couple of webinars that you had with your team leads, is clarifying what is the question you're trying to address here in your clinical trial. Because if you can't define that, then you really can't flesh out a protocol, right? You have to get that nailed down. What exactly is the question you're looking at here? And then the rest of the design should be set up in a way to show that, right? Your sample size should be set up in a way to justify that you have the ability to answer that question, right? And various situations of what you would think would happen. Doing this in smaller trials, like more learning phase designs, doesn't change the need to have these requirements. It just makes it somewhat more difficult, and you may have to have conversations to figure out how you would go about that. And that's why I say in a lot of ways, study planning, study design is more complicated in phase 2 because there's lots of different scenarios to consider, and you really need to have ongoing conversations early in the process with your statisticians and other collaborators to come up with a design that's appropriate. And one of the things that was a common theme from all the networks, if you look at the studies that are being done in the networks, many of those have been in the planning stages for 2, 3, 4 years before they ever get funded. There's a lot of upfront work that it takes to figure out what's the best way to do a design. And the more you can keep those conversations going, the better you'll end up with the design. So talking about briefly, I want to go all the way back to like phase 1 studies. This is a couple of common things that come up there. One of the things with phase 1 studies, particularly if you're doing dose finding, which is a common thing that you would do in this type of study, these are generally small, and you might be looking at multiple doses, looking for the maximum tolerated dose, where you're trying to see, how high can you go. Often these are in healthy populations, where you're trying to see how high can you go in a healthy population, where we generally think, not always, but in most cases, that the higher you go in the dose, potentially the higher the safety risk, but also the greater the chance for efficacy. And so what you're trying to get a sense of is, what's kind of the maximum dose you can go to, which kind of defines then in moving into subsequent studies, where should you be targeting the dose to try to find an efficacious dose. And one of the biggest, I think, confusing points, because these trials are so small, is that, and this gets back to the simulation question and the point that Roger made earlier in doing it under different scenarios, is just because your design says it's the maximum tolerated dose doesn't mean it actually is the maximum tolerated dose. So one of the ways you want to assess, in phase 1 study is you can run simulations or run calculations under various scenarios and see how often does your design find the correct MTD, how often does it go over, which is often termed overshooting, which is what we like to avoid, where your design is saying a dose is tolerable that's much higher than the known if you run it under simulations, which means you're taking a dose to further studies that's potentially too large, where you might see safety concerns that would complicate things when you put in additional patients. Generally, where you would be interested in, one of the things in defining that is what level of toxicity you're willing to accept. And you often would define your DLT. So you're not looking at any adverse event, you're usually defining what are the really bad things. Now, in a perfect world with unlimited resources and no human subjects oversight, which will never happen, you just randomize people to all the doses and see what happens and get lots of data. That's not necessarily how these would work. And even, you don't just start kind of randomly going to different doses. Typically, you'd have to start very small and slowly work your way up, right? You're going to start with a small dose, typically based on animal data, usually a dose that's well under what you think would be the MTD from the animal data, but you confirm that it's safe and you would step up. It's often done in cohorts of, 3 is the magic number. You can do it with other sizes, but 3 seems to be most common. Where it gets really confusing, this is particularly in neurology, is there's a very popular dose finding design that is easy to understand and doesn't really require a statistician. That's the 3+3 design, which is very common, particularly in oncology, where you treat patients in groups of 3, and it's a very simple rule. So if none of the 3 have a DLT, you move up to the next dose. If 2 or more do, then you would move down or stop depending on where you are in the process. And if one of the 3 does, you treat another 3 and see how they do, and that defines where to go. But it's a very prescriptive, easy to define thing. Any of your statistical colleagues or other clinical colleagues who have used it could sit down with you for a half hour here at the course and explain how the 3+3 works, and you could go home and implement it. So it's a very popular for a variety of reasons. One, it's been used a lot in oncology. 2, it's very easy to understand. There are other type of approaches that use like Bayesian modeling. The continual reassessment method is one of the most popular, which uses an assumed model and kind of updates the data and takes advantage of all the data. So there are advantages of CRM that have been well documented from like a statistical and operating characteristic perspective, but there are also important advantages that are in some ways related to limitations of the 3+3. So it's very common when I talk to investigators who want to do this in some neurology setting, they're familiar with the 3+3 design because they've seen it, it's used a lot in oncology, and because it's easily understood, they feel like it would be appropriate to use for their neurology study. For instance, one example that I will give is one of the NeuroNEXT studies that we're involved with is an acute stroke study where they're doing a dose finding study with a very preliminary agent that is looking at, can it benefit treatment of stroke, but they're looking at dose finding, they're looking at safety here. The dose limiting toxicity that you would look at for this type of neurological stroke study is going to be things like major bleeds, right, that you're interested in. The big distinction between that and one concern with using the 3+3 in that type of study is in the oncology setting, it's kind of optimized where, when you're treating cancer using these chemotherapy agents, a lot of bad stuff happens with chemotherapy. Your range of what you might accept is typically with the, in the 3+3 designs used in oncology would be in the 30 to 35% range. That's kind of where the 3+3 comes, right? 1 out of 3, that's about 33%. That's about the level of toxic things that you'd be willing to accept to move that drug forward in that oncology chemotherapeutic type of setting. If you're dealing with a stroke drug where 10% might be the threshold of what you're willing to accept, that's going to be a horrible design, right? If you think about it, if any of you have had a statistics course, right? Think of the binomial distribution. If you treat 3 people and your true rate of a DLT is actually 10%, your probability of seeing at least one have that DLT is pretty small, right? Even if it's 15%, so even higher, it's still small. So if you use the 3+3, you're likely to overshoot. And you're going to end up thinking the dose that is your maximum tolerated dose is probably higher than your actual maximum tolerated dose because it's not really calibrated to the situation you want. It was developed in an area where you're willing to accept more risk than you may actually be willing to accept. Now, you can say that. It often takes a number of conversations to convince investigators of where that can happen. And one of the things for studies like this, when we worked with the investigators, and this was a small biotech company who came to us and they originally wanted to use the 3+3. And we had several conversations trying to explain this, but it takes a while to get there. And so what they had 4 dose levels. Again, they're looking at these things with like major bleeds. And what we ended up doing was running a simulation study to illustrate to them how it would potentially be problematic. And so we looked at, again, covering the range of dose. All doses were safe of the 4 doses, the lowest, the second, the third, the fourth, and all, none of the doses were safe. So we looked at basically all 6 different possibilities of outcomes you would have and made like various assumptions of what the risk would actually be to kind of meet that criteria. But what you see here are a couple of different things. So if all doses are safe, it really doesn't make a difference what you use. Where you really see the benefit is if you actually have a safety concern, the CRM does a much better job of finding that. Partly because the risk of seeing any DLTs in something with a very small actual rate is small, the 3+3 is always going to go to the largest dose in most of the instances, regardless of what the truth actually is. So even when like one of the middle doses is the true MTB, the 3+3 is probably going to tell you that the highest dose is safe. And you can see that by looking at the second column, which is your probability of overshooting. That's choosing a dose that's higher than your actual dose that because this is a simulation study where you actually know what the true value is. And so this just confirms, as long as there was no risk, it doesn't matter if you use the 3+3 or the CRM. But when there actually is some level of risk where the highest dose is not safe, then it's going to make a big difference in that the 3+3 because it's always going to go very high in the thing. So having tables like this, having conversations with the investigators help to really clarify that case. In terms of how it works, so you assume some general model that you have at the start, and then as the groups come in, you update your model just to try to illustrate. So this is kind of the original assumed, although you start at the lowest dose. We actually saw, so you can see here in the first cohort, you saw a DLT, so it makes a big jump down, right? Because you have very little data at that point, so it's going to make a big difference in terms of what that does. Over time, right, you get the next one, it goes up, it's going to iterate back and forth, and you can see at the very end, this is kind of what you end up. This is a plot that shows through all iterations of the cohorts how it moved, where the red line represents the originally assumed curve, and the black line illustrates the curve that was observed at the end of the study. So in this instance, the highest dose was deemed to be the maximum tolerated dose. It took a while of transferring back and forth in order to do this. One other interesting aspect of this study is we ended up we had about 100 patients in the study because there were some secondary objectives that the company wanted to get some data on, whereas most dose-finding studies tend to be in the 30 to 35 range. And if you look at what would have been the maximum tolerated dose at one of these lines, if we had stopped around 30 to 35, you get a different answer than what you get with 100 subjects. So it's kind of interesting in terms of this discussion, should we be doing larger learning stage studies if we really want to get better answers? It's kind of a separate discussion. And so these results have been presented at ISC last year and are currently in the process of the papers under review. So kind of moving into phase 2, that was really early, which was probably the earliest phase that we've been in NeuroNEXT. What's more of the things that you would look at would be in phase 2 type studies, where now you kind of come for phase 1, you're looking at this kind of proof of concept, and phase 2, it's really difficult in some instances to come up with a question that's testable, where you could have the methodology in place. There are some things that you should avoid, and these are, what I pulled in is 3 of the most common things that we've seen both within NeuroNEXT and in working with other investigators. Number 1 is if you really want to kill any chances of getting a grant funded with NINDS, just call it an underpowered phase 3 study, right? That is probably, that's like a swear word in study section, clinical trials, and NINDS notation, because basically what you're saying is, I want to do the phase 3, I don't have all the resources to do the phase 3, so I'm going to pretend to do the phase 3 and just do a small version to get data to do the phase 3, but I don't really have a question, right? Because I can't answer the phase 3 question. That's a horrible approach. Never do that, right? That's not something you should look at. Now that one's a little intuitive. There are others that can come up as well. So there's temptation sometimes to, like, you know, if you don't know what your outcome is, which comes in some disease areas, and so you want to not miss it. So you throw in a bunch of outcome variables and you say, if I have a positive result on any of these outcome variables, I'm going to go forward, right? Again, you could run simulation studies and show you're going forward, right? And even if the drug doesn't work, just by chance alone, you might see a benefit on one of these predictors. And so that gets back to, okay, what question are you really addressing here, other than pretending that you know more than you do? And one of the things where there's more pushback against situations like that is there's been a number of histories, not just in neurology, but a lot in neurology, where you have these types of phase 2 studies that can be interpreted as positive. You get to phase 3 and the phase 3 studies fail. That's a huge investment when you get to that point, both in terms of the cost, the resources. It's also devastating to patient communities, right? They're excited, especially if it's an area where there's not many treatments. They're excited because of all of this promising. They feel like it's got a lot of promise. The phase 3 study fails, and then they're kind of back to nothing, right? And so that's a very difficult thing you know, for the communities to address. It's like they get their hopes up, and then the rug is pulled out from under them. The other aspect is, you know, you have limitations on sample size due to budgetary constraints. No matter what you try to do, you can't really answer a question, so you're going to try to do what you can do with the sample size. And that's a tricky one, because if you really don't have a question to answer, and it's just because of the resources you have, then at one level it's probably not a fundable study, and that, you know, it just might not be feasible to do the study to address the question. And the other part is, when you're underpowered, if you can't really address it, the results are somewhat subjective. And every single one of you in here could look at results from a study in your disease area if you think the drug works and see those as positive results. Where somebody else might look at those same results and be just as convinced that it's a negative result, right? I mean, we see patterns in what we want to see, and our own biases in some ways reflect how we look at results. In terms of types of phase 2 studies, some of the general ones that have come through, and these are I tried to categorize them in kind of the simplest one. There's areas where you would use different endpoints, and then there's areas where you would use the phase 3 endpoints, but perhaps do it in a slightly different design. I'll quickly talk about 3 of those. So there's safety tolerability designs. One of the things, and this is something that has come up commonly over the years in areas where you don't really know a lot about the clinical outcomes to even try to design anything to answer a question there. It's really uncertain, but it's so early. Maybe this is one of the first kind of phase 2 studies. One of the key questions that you might be willing to ask, instead of just collecting data, is tolerability, right? Will people stay on the treatment? You know, is it safe? Is it tolerable? And so that, at least you have a question to answer, right? If you find out that in a simple study that less than half the people are going to stay on your drug over a 2-year period, it's probably not feasible to do a phase 3 study, right? You can also collect data on some of your endpoints and get some information while you're doing that. In one of the NeuroNEXT studies, so in 105, is a company with Azavan looking at this this drug to treat tolerability in irritable subjects with Huntington's. That's exactly what the primary outcome is. It's looking at the tolerability of subjects over a 12-week period. And is looking at that, so there's two different doses and placebo, and what you would define there as tolerability is, do they complete the 12-week period on drug, right? So the primary would be, are they falling off for various reasons? It could be because they're having adverse events, they have to come off drug. It could be that they're just dropping out of the study. And so you have like a secondary where you actually look at, are they dropping out for tolerability related to drug? But in some sense, if they're not finishing the study, they're not finishing the study. And you never know, if they drop out, maybe it's because of the drug and you just didn't capture it, because they didn't tell you about it. And so you want to be as conservative as possible in addressing that, but also have secondary analyses to look at that. So that's one when you really don't have a sense of what to look at from an endpoint. The other one that comes up some, and this will hopefully be more common in the future as we get better biomarkers, better surrogate endpoints, which is a huge need in a lot of different areas, would be a surrogate endpoint design, where maybe the phase 2 study you can do, you would use a surrogate endpoint to look for an effect on that surrogate, and if you saw that, that would then justify doing the larger study with the clinical endpoint that you would be interested in. The NN102 study used a design like this. So this was an intervention looking at patients with primary progressive, secondary progressive MS. And it was using a surrogate endpoint of brain atrophy, where the idea being if you could show that the drug slows brain atrophy, and it would then be thought that you would see clinical benefit with respect to the drug. You would need a larger study to show the clinical benefit, so this was kind of an intermediate study. This was like 250 subjects, so it wasn't small, but as opposed to like the 700, 1,000 people that you would need to show the clinical benefit. And so what we saw from that study is, so this is a general plot, so it did show that there was a slowing of the reduction of brain atrophy associated with the drug that was statistically significant. The question then, now the next question is it clinically meaningful? And you can see if you look at the EDSS, there was some trend towards benefit that you saw in the clinical endpoint here. The study was underpowered for that, so it's not statistically significant. And kind of the next step is now this kind of provides evidence to take it to phase 3, and the company that's involved is moving forward with kind of planning the phase 3 to follow up on this to see whether you can confirm the clinical benefit, which would be needed to get approval to use that in this disease space. The last type of study I'll talk about is a futility design, where, and this came up some yesterday in the discussion, was really kind of a non-superiority design. It's a really clever design. It's got a horrible name, and people hate it when you first bring it up because nobody wants to show that their study is futile, right? So you have to get past that initially. But what you're looking at here is if you think about and you do a test comparing like a drug to a treatment, there are kind of 3 broad outcomes you could get, right? That the treatment is worse, that the treatment is better, or there's this middle ground where it's not statistically significant, maybe it's a little better, maybe it's a little worse, but it doesn't meet your meaningful difference. When we're doing the typical test of superiority, we're trying to determine that it falls in this range out here, right? That it's better, it's not nearly the same, and it's not worse. The non-inferiority test just looks at, it's kind of a gatekeeping screening type tool where you're doing a test to determine, is it clear enough from this phase 2 that we are not going to be out in this range to not justify the phase 3, but we're not trying to show that it's in that range. So in other words, with a futility design, I think it's a non-inferiority, I apologize for that. I mean, a futility design, if you reject it, then you're showing that you're out here where it's unlikely to benefit because the drug is either no better or worse than treatment, and it doesn't make sense to follow it up. You're unlikely to see the clinically meaningful effects you would need to see in a phase 3 study. Versus if it might be, so not rejecting it again doesn't prove the null hypothesis, which is always the case. So it doesn't mean that the drug works. You would have to do the follow-up study to determine does the treatment work or is it just a little bit better but not enough to be clinically meaningful. To illustrate that. Battery is running low. It's not working. Where's Joy? Says the battery is running low and it stopped working. So I can try to talk off the test. There, let that now work for a minute. Hopefully that I'll try to do that. To illustrate that, so in NIND 103, which is my myasthenia gravis trial, we actually did the futility design. And what you're looking at there is, you're kind of thinking of, again, it's what effect would you power in the phase 3 study to be meaningful. So if you assume, for instance, in this case, if you expect, in this case, we were looking at prednisone sparing. So the endpoint was, can you get at least a 75% reduction in prednisone from where they started to where they are at the end of the trial, looking at, they were randomized to rituximab or placebo. Expecting about 40% of placebo subjects would meet the criteria for reduction. And if you were planning this like a phase 3, then meaningful difference here was a 30% absolute increase, so going from 40% to 70% on treatment who would achieve that reduction. Okay? So your null hypothesis here, which is slightly different from your typical null, is that you have at least that 30% absolute benefit. So assuming the placebo group is 40%, that's saying the null is that the rituximab group would have 70% or higher response, is your null. Your alternative is that is not the case, right? So rejecting the null here is saying that you have enough evidence to conclude that you're far enough away from that 30% benefit that it's unlikely you would see that in a follow-up phase 3 trial, and it doesn't make sense to follow that up. Not rejecting it doesn't imply that. It's fine now. It said the battery's running low, so after this, you might want to check it. Is it plugged in? Maybe. Okay, sure. If you don't reject it, then it means it could be 30% or greater, but it could only be like 5%, 10%. You're just not far enough from 30% to reject. So to illustrate this pictorially, and again, this is the kind of things that I think helps in terms of illustrating to the investigators how the futility design breaks out. So with an alpha of 0.1, you can see here that so assuming the placebo rate is 40%, if the rituximab rate is 70% or higher, that's the green region that you see here. The probability of declaring futility when that's true is 10% or less, right? That's our type 1 error. That's what we want. If it's 40% or lower, that would be the situation where the treatment group is the same or worse than drug, and we want to declare futility when that's the case. That's the red region, which is in the 70, 80, 90% range. That's what we want. We have this middle ground, this yellow ground, where it's somewhere between 40 and 70. We're not going to reject for futility. That's the range where, what we would have at the end if we don't declare futility is we think we're likely somewhere in the green or yellow range. We don't know. The justification for the phase 3 study would be doing the study to determine whether that's the case. Do we actually fall in the range of benefit or not? And so this is kind of pictorially how this would be set up, and what I found helps in describing things to investigators. What we found in the study there was some slight benefit in the rituximab group, but we actually met the criteria for stopping for futility. So this study, it was presented at AAN this year, met the futility threshold, which says that it's unlikely, if you continue to phase 3, it's unlikely you would see this 30% benefit of rituximab with respect to prednisone sparing in the way it was defined here, which means it would be hard to justify that phase 3 trial given these results. It pretty much concludes that you're far enough away from that effect in order to see it. So as kind of a study, this wasn't like your typical underpowered study where you might see that and look at a wide confidence interval. It was powered to detect that, and you end up with a more clear answer at the end. And then I'll conclude, I pulled dog pictures in as we're supposed to. This is Luke. This is our Yorkshire Terrier who hangs out with golden retrievers and thinks he's a Yorkshire Retriever because I actually think he thinks he's about 80 pounds. And he actually weighs 4 pounds. So I have to take questions.
Do many studies use, aside from the 3+3 on the fixed dose, have you seen a lot of variability? So if the toxicities are different and you're willing to accept the curing the mouse, would anyone ever do a 10 or?
There are ways to get around, yeah. I mean, so you could do like 10 plus 10, 12 plus 12. The other side, though, is in a lot of ways, so there's two sides to that. I mean, one, the Bayesian adaptive designs are a little better statistically because they incorporate all the data into the model each time, whereas like with the 3+3 or the 10+10, the rule is based on that cohort at that dose and doesn't take into account the other data. So it's a little less efficient for that aspect. The trade-off is you need more statistical computational support to update these models each time, but that's becoming less and less of an occurrence now. So in general, the Bayesian type models are more efficient because they're using the totality of the data. You're taking the full, model dose response each time as opposed to what happens for each cohort. But there is still, it's slowly becoming more acceptable, more common to do that, but it's infrastructurally more computationally intensive to do.
With your marker of reduction of prednisone dose, most people have a plan for increasing prednisone. Would another measure be increasing the prednisone dose, like say how many times you can go in that you have to increase it?
Well, we have a secondary in that study. It wasn't like with the primary, which is similar to that, but like how many times do people have relapses?
Yeah.
Which they obviously had to increase the dose for their relapse, but they might increase it for other reasons that we captured there. But yeah, I mean, it's kind of there's a lot of secondary questions to ask, like how many people got down there, did you get down there and have jumps along the way, versus that. The main thing we looked at is relapse, not necessarily increases for different reasons.
And then the rituximab group, whether it were times we had to increase the prednisone dose, or is that not on it?
It's analyzed. It's not in the primary results, and it was pretty comparable, I think, in the two groups. I have to go back and look. That's my recollection.
Can you give an understanding or describe the difference between utility design and adaptive design with early stop before utility?
Sure. So they're structurally similar in concept. It kind of gets to what tools you use to address those. So, and what the ultimate thing is. So if it's an adaptive design with like a phase 3 with utility, then the idea is you're looking for confirming. If you find out like somewhere in the middle that you're far enough away from that, that's going to unlikely that you would pull the plug and not continue. If that's not the case, you would continue going on to the end, right? So the utility design is kind of strictly phase 2. The intent is not to show efficacy because you're limited in terms of how you would do that. You could put like a futility type hypothesis inside as an interim futility monitoring in a standard clinical trial in kind of the same way. But the intent of like the biggest difference in the two, the futility design is really just looking at kind of the futility is the main analysis you're doing. It's not a step along the way. There's no intent to go forward and do the confirmatory. Although you can combine the concepts together in some way, but that's not typically the way it's done in these types of things. Does that make sense?
In the surrogate endpoint designs, how do you, in order to pick up the endpoint, does it need to be associated with the endpoint that you're going to choose for your phase C trial?
Yeah, and that's the biggest probably discussion point in those is ideally you have a well-validated endpoint that you know is predictive, right, of the clinical endpoint. What I've often found when you get into those discussions is some people have strong opinions that it is, some people have strong opinions that it may not be, but there's really not the pure validation work at the level that you really need to do that. And so it becomes somewhat subjective, and how well that would do with the screening tool is going to be a function of how correlated is that. Is it a real surrogate, or is it just something that's somewhat correlated or predictive of the endpoint in some way? It's the biggest complication, I think, in terms of using those, not just this, but biomarkers in general, is that we kind of need. It'd be nice if we had more research kind of standalone development and validation of biomarkers, which is getting discussed in areas that is not necessarily funded at the same level as clinical trials. And you kind of need those tools to inform the clinical trials. But it's kind of a catch-22. There are some areas where you have really good biomarkers. There are just not many in neurology right now.
There was a lecture online a while back reading on pilot studies looking at the feasibility of other trials. And in that reading and the lecture, they were saying if you keep the logistics the same from the pilot to the full-scale trial, and actually include the data from the participants in the pilot in the full-scale trial. Do you agree with that? And would you say the same for utility studies?
So two thoughts on that. One, I'd have to take a closer look at the paper before I can go forward. Number one, it's kind of a moot point, and then I don't think I've ever been involved with a study where the main structure stayed the same like the earliest time. I don't even know that I've ever seen a clinical trial that stayed the same with the means at the end of the trial. The biggest thing alone is everybody's overambitious about what they can recruit and tight inclusion and exclusion, and then you run into recruitment challenges and they start to relax. That's a common thing. But that being said, you have to be careful about combining data, and this is one of the things like with adaptive designs that comes up in general, is there's a lot of advantages of adaptive designs and sharing data across different places. There's a lot of potential bias you add in as well, right? I mean, one that's pretty common is if you're doing, say, the phase 3 because the phase 2 was positive, and you just combine those data sources together and do your analysis at the end as if that was all just one data set, that's a biased answer, right? Because you're only doing it because you like the result you got from phase 2. There's an inherent bias in terms of doing that. The same thing comes if you're choosing doses in an adaptive design. And so one of the things that any type of combination of any type of adaptive design is doing simulations or assessments in place to see A, what's the level of bias, is it a level of concern, and then equally important, are there methods in place to correct for the bias? So anytime you're combining data sources, which in some rare disease settings you might try to do, but you can't just do that and not take into account the data-driven aspects of that you can run into. In terms of combining it all the way through, I would think that would be unlikely, just because, like I say, it'd be hard to, it's kind of an academic exercise if you had to guess. And practically, I think it would be very difficult to ever see a case where that would be true.
I noticed in some of the results slides here, they're presenting 90% confidence intervals. Is that because in some of the earlier or learning phase trials you're willing to accept more type 1 error?
Yeah, I mean, that's one of the balances in terms of sometimes to like try to have the ability to answer the question, and you're in some ways because you don't want to, so often, and it's kind of consistent, often you're willing to have a higher type 1 error to better control the type 2 error. And a lot of this depends upon the investigators. And so point 1 is not that uncommon for phase 2 studies, because it's like, it kind of goes to the sponsor, whether you're willing, which error you're willing to accept. And there's nothing magical about 0.05 where it has to be. But you might be willing to accept a 0.1 type 1 error to make sure you have a high level of power in terms of doing it. I would rather, personally, like those people, I would rather have 0.1 type 1 error and 90% power for a phase 2, as opposed to like if the trade-off is 0.05 error and 80% power. The reason for that kind of gets into like the adaptive, so I'm interested in adaptive designs, but inevitably in trials, particularly in academic trials where you're trying to get it funded, you end up with lots of different plausible scenarios. And a common like grantsmanship issue is you make realistic but optimistic assumptions, right, to get the budget and the sample size in a range that's not going to cause people's intent to come up. But because of that, we're way more likely to be off in our assumptions in a way that leads to us being underpowered than overpowered. It's not symmetric in the way we're off. And so I tend to want to like power studies at 90%, because if there's a little bit of, you're off in certain directions, you might go down to 80% and you're still okay, versus if you're at 80, you drop off into like the 65 and 60% really quickly. And if you look at power curves, they're sigmoidal shape. And so 90% you're more on a flatter region, so you can be off more in your assumptions and not drop off. If you're around 80%, you're near what one of my advisors termed a slippery slope, right? So where you end up with a much steeper slope when you're off at the same level. And so as much as possible, I try to push people